You know, the device you're watching this on right now, the building you're in, maybe even the change in your pocket, they all depend on a really special family of elements. Today, we're going to pull back the curtain and uncover the secrets of the D-block metals. These are the unsung heroes that literally built our modern world.
I mean, just think about how versatile these are. Iron gives us the strength for skyscrapers. Copper gives us the conductivity for our power grids. And for thousands of years, gold and silver, they've been the ultimate symbols of wealth and beauty. These aren't just materials, they're the cornerstones of human civilization.
So they all share this amazing set of properties: strength, conductivity, all that good stuff. But what's the secret sauce? What's the common thread that ties all these powerful metals together? Well, that's exactly what we're about to find out.
All right, first up, let's just take a moment to appreciate the incredible historical impact of this group. I mean, from the Bronze Age all the way to the high-tech alloys we use today, these metals have always been right at the center of human innovation.
So what is it that makes these elements a family? Well, officially they're called transition metals, and the reason why is surprisingly specific. It all boils down to this one simple but really powerful idea: being incomplete.
Okay, so here's the official definition from IUPAC, which is kind of the United Nations of Chemistry. The key isn't just where they are on the periodic table, it's that they have an incomplete D subshell. Think of it like a puzzle with a missing piece. Their outermost electron shells just aren't completely full, and that one tiny detail, well, it changes everything.
And this slide shows that rule in action perfectly. Over on the left, you've got scandium. In its normal state, its D subshell has just one electron. That's obviously incomplete, so boom, it's a transition metal. But then look over at zinc on the right. Its D subshell is 3d10. It's completely full. So even though it lives in the D block, by the official definition, nope, not a transition metal.
Now, this idea of being incomplete isn't just some boring classification rule. It is the very source of their power. And to really understand why, we need to dive in and look at how these orbitals actually get filled up with electrons.
So as we move across this first row of the D block, a really clear pattern starts to show up. Scandium is 3d1, titanium is 3d2, vanadium is 3d3. So you'd think the next one, chromium, would just follow the pattern, right? Logically, yeah, we just add one more electron to that d orbital and get 3d4. It makes perfect sense. It follows the neat and tidy pattern we just saw.
But chemistry just loves to throw a curveball. This is what actually happens. An electron from the lower energy 4s orbital gets promoted up to the 3d orbital. So instead of 3d4, we get 3d5. But wait a second, why would an electron move to a higher energy level? That seems to go against everything we know.
And here is the secret. Nature craves stability. It turns out that having a d orbital that is exactly half full, like chromium's 3d5, is an incredibly stable, low-energy state. You could think of it as a perfectly balanced system. The atom is just more comfortable this way. This powerful drive for stability is a fundamental rule breaker in chemistry.
Now, this unique electron behavior isn't just some quirky little exception. It directly leads to the physical properties that make these metals so unbelievably useful in the real world. Because all those d orbital electrons are available for bonding, transition metals form these incredibly strong connections between their atoms. It's why they're so hard and strong, but you can still stretch and shape them. It also means it takes a massive amount of energy to melt them or to pull their atoms apart.
And you can see this trend so clearly on this chart. As we move toward the middle of the D block, where you have more of those unpaired d electrons ready for bonding, the melting points just skyrocket. It's kind of like having more hands to hold on to your neighbors. The more connections you have, the harder it is to pull everyone apart.
We see the same exact pattern with the enthalpy of atomization, which is really just a fancy way of saying the energy needed to break the solid metal down into individual free-floating atoms. And once again, the peak is right there in the middle, showing us exactly where the bonds between the atoms are the strongest.
But the quirks of these electron configurations, believe it or not, don't stop there. They lead to one of the most fascinating and, frankly, weirdest effects in all of chemistry, something called the lanthanoid contraction.
Okay, so let's start with a basic rule of the periodic table. As you move down a column, you're adding entire new shells of electrons, so the atom should get bigger. Simple enough, right?
Now check this out. Hafnium is directly below zirconium. It has a whole extra shell of electrons. It should be significantly bigger, but it's not. it's actually a tiny bit smaller. How is that even possible? This just breaks the rule we thought we knew.
The answer lies in the elements that come just before hafnium, the lanthanides. They are filling a special set of 4f orbitals. And it turns out, f electrons are just terrible at their jobs. They're really, really bad at shielding the outer electrons from the pull of the positively charged nucleus. Imagine a weak umbrella in a strong rainstorm. As you add more protons to the nucleus, that powerful pull just sucks all the electron shells in tighter. And this contraction almost perfectly cancels out the size increase you'd normally expect for hafnium. It's wild.
So let's bring it all together. The incredible strength of these metals, their super high melting points, their tendency to bend the rules for stability, and even this bizarre way their atoms shrink, it all comes back to one single thing: the unique behavior of electrons in their partially filled d orbitals. That is their ultimate secret.
It really makes you wonder, doesn't it? If the simple drive for stability, right down at the atomic level, is powerful enough to create the most useful materials in our world, what other fundamental principles are out there, quietly shaping the universe in ways we haven't even begun to discover?